Okay, good morning everyone. My name is Victor Trejo and I come from the Center for Material Forming from Paris in France. And my talk today is entitled Microscopic Strain Calculations at the Onset of Coalescence in Nodular Cast Iron. Okay, just to put things into context, what is ductile fracture? Well, here we have a stress strain curve for two materials, one damaged material and one undamaged material. And we see that our damaged material loses its load-bearing capacity and presents an earlier fracture. This is the consequence of damage at the macro scale, but what happens at the micro scale? Let's imagine this is a tensile specimen, and we will typically have a population of second phase particles or inclusions. And if we start deforming our material and we deform enough our specimen, we will start observing the nucleation of very small voids that will appear either by particle fracture or by the cohesion of the particle matrix interface. If we deform our material further, these voids will grow and eventually they will be so big that they will start touching each other, so they will coalesce. And this will produce the macroscopic or final failure of our specimen. And this is what we call the micromechanisms of ductile fracture. So void nucleation, growth, and coalescence. And if we take a look at the fracture surface, we can see evidence of these micromechanisms. So this is the object of this study, the micromechanisms of ductile damage. First, I will present the general methodology of the project. This project is a collaboration between three different laboratories. The Material Center from Paris, the LMT Cachan from the ONS Cachan, and the Center for Material Forming, again from Paris. The methodology is a combination of three different techniques: laminography, digital volume correlation or DVC, and finite element modeling. Okay, with laminography, what we will obtain is three-dimensional images of our microstructure. And if we do different scans during a mechanical test, we can observe the evolution of our microstructure during the ductile fracture process. This information can be used as an input for the digital volume correlation, and then we can calculate three-dimensional kinematic information. That means three-dimensional displacement fields and strain fields. And we can use all of this information to carry out finite element simulations with immersed microstructures and realistic boundary conditions. Okay, so first, what is laminography? Laminography is very much like tomography. In tomography, we have an X-ray source directed at a stick-like sample. The X-rays will go through the sample and onto a pixel detector. And if we rotate our sample and do several scans, we are able to produce a three-dimensional volume of our microstructure. Laminography is very much the same, except that it helps us eliminate the restriction with respect to the geometry. So in laminography, we are able to study flat specimens. We can study specimens such as this one. This is a tensile specimen, and we are taking an interest here in this small region. We scan this region and we obtain this three-dimensional volume here of our microstructure. And to give you an idea of the scale, this black line here is 100 micrometers. Okay, so for digital volume correlation is, let's say, an extension of digital image correlation in 3 dimensions. So what we will do is to try to correlate an undeformed configuration F with a deformed configuration G through a three-dimensional displacement field. We will solve a global minimization procedure to obtain this displacement field, and then we can calculate three-dimensional strain fields. Okay, for the finite element modeling, I won't go very much into the details, but I wanted to try to convince you that we are able to handle the topological events that occur during ductile damage. That means that we are able to model particle fracture, nucleation by particle fracture, nucleation by debonding of the matrix particle interface, that we are able to model coalescence by internal necking and or coalescence by using a physical criterion that can be based on stress, strain, or a damage parameter. And with this, we can carry out simulations such as this one here. This is a three-dimensional simulation of a representative volume element with a digital artificial microstructure. To the right, we see in gray the nucleated void. They will nucleate, grow, and coalesce with each other. And to the left, we have the equivalent plastic strain. And you can see that we reach very high values of plastic strain. Okay, so what was the purpose of this methodology? The purpose was to try to carry out realistic simulations of ductile fracture. That means simulations with immersed microstructures and realistic boundary conditions. So we can take, for example, one piece, one portion of our volume here. We immerse it into a finite element mesh. And we will apply on the boundaries an heterogeneous displacement field that comes from the digital volume correlation. And we obtain things like this. So in here we have a sequence of images of a microstructure, of a simulation. So we have in gray the voids. It's a simulation of nodular cast iron. And we have three perpendicular planes where we are showing the equivalent plastic strain. We see that it's 0 in the beginning and then it evolves, it reaches high values. You see the evolution of the microstructure, and you might notice that the planes change their shape and they are no longer planes, they are curved planes. And this is because we are imposing heterogeneous displacement fields. Okay, so we would like to apply this methodology to study, for example, void coalescence, but it would be nice to validate our results first. So to do that, we will try to take an interest on two particular observations. This is a two-dimensional slice of a laminography volume. So here we have coalescence by internal necking, and here we have coalescence by the void sheet mechanism. And what we will do is that we will place one probe, one volumetric probe in each of the corresponding intervoid ligaments. So this one here corresponds to the void sheet mechanism, and this one to the internal necking. And since we have the results from the DVC, we have the DVC strain fields, and we will compare those results with local strain measurements from the finite element simulations. This is what we are doing here. So here we have the local equivalent strain during our simulation. The orange curve is the results from the simulation, and the blue curve is the DVC results. We see that we have a very good match between the two curves, except at the end of the simulation where the strain in the DVC results starts to increase very rapidly, and the finite element simulation isn't able to capture this acceleration. This was for the first probe, which is here. So for the void sheet coalescence. And for the second probe, we have this. Okay, so we have also a very good match until here maybe, and then we have this huge acceleration, which again is not captured by the finite element simulation. And you might notice here these error bars, which are a lot larger than what we saw here. Here they were barely visible. And the reason why we have these bars here is that if we go back and we take a look at the probe where we are seeing the strain, this probe is in a very small intervoid ligament, and it's big with respect to the ligament. So one portion of the probe will be actually inside of the void phase. And why did we do it like this? We did it like this because we are trying to validate our results by comparison with the DVC. And the shape, location, and size of these probes actually correspond to the geometry of the DVC elements. And this causes that, I didn't mention it, but these error bars, they are related to the uncertainty that comes from the immersion of the microstructure. So since we are very close to the interfaces, we have a very big uncertainty. Okay, so maybe we can, for the moment, conclude that we have a very good match between DBC and FE strain measurements. But is there some way that we can improve our results given this big uncertainty? So maybe we can try to take advantage of the finite element spatial resolution. And this is what we try to do here. We try to do a sensitivity analysis with respect to the size of the probe. So these red cubes here are the initial probes for which we already saw the results. And then we have smaller probes in the middle, inside of them, a green one and a blue one, and we will see what we obtain. So for the first probe, we obtain this. The green one corresponds to the largest probe, and then when we decrease the size, we don't see a huge change for this probe, and we see that we converge very quickly in terms of spatial resolution. The reason is that this probe is located in the middle of a large intervoid ligament, and the strain field is somewhat homogeneous and diffuse in here. In contrast, for the second probe, we see this is the original results that we had seen before, and as soon as we decrease the probe size, the strain measurements increase considerably. Just to have an idea of the order of magnitude of the increase here, let's say that roughly we were in about 35% of equivalent strain, and here we reach almost 100%. So this difference is very significant. Okay, so I would like to say that we have validated our finite element strain measurements, and that we have learned that sometimes our finite element strain measurements are more sensible because they are able to take a look in intervoid ligaments that are very close to the interfaces. So we can take advantage of the spatial resolution of our finite element simulations. And now, since we would like to say that we have validated our simulations, we want to try to extend our study and see if we can formulate eventually void coalescence criterion at the microscale. And for this, we are studying right now 18 different positions where we identified the occurrence of coalescence during the simulation. And we are taking a look at local measures of strains in the different intervoid ligaments. We are studying the evolution of the intervoid distance for all of these ligaments. And the objective, as I just said, is to try to find a coalescence criterion at the microscale that could eventually be transferred somehow to the macroscale. And with this, I conclude my presentation, and I thank you for your attention.